Periodic trends. This video is going to be a bit longer than most of my videos, but I think it's helpful to walk through all of these concepts together in one video rather than trying to separate them into several. Let's first talk about what we will cover. Here I've listed out all of the periodic trends that we're going to go over, and the arrow points in the direction of the increasing trend. We'll come back to this after we've gone over them all, but this will give you just a little bit of an overview of what we're going to cover. What do we want you to get out of this video then? For each of the trends on the previous slide, we want you to be able to rank the elements, explain that ranking, and because the trend says so is not an explanation, you'll need to explain the reasons behind the trend itself. And then we want you to be able to explain why the exceptions for the trends exist, which will include using electron configurations to be able to explain those exceptions. So let's get started with effective nuclear charge. Effective nuclear charge is the charge that the electron feels when both the actual nuclear charge and the shielding effects of the other electrons around it are taken into account. When we're talking about periodic trends, we need to remember that both the nucleus's protons and the other electrons have charges. Let's use the Bohr model of an atom to talk about how this works. Though of course we know that this model isn't accurate with atoms with more than one electron, it is a helpful simplification for our purposes here. The electrons that are between the nucleus and the other electrons shield those outside electrons. So electrons in the first shell will shield electrons in the second. And then the electrons in both the first and the second energy levels would shield those in the third, and so on all the way out. Let's switch to talking about the horizontal trend though. Within a period, or in other words, a row, as you look at the row from left to right, you'll see an increasing number of protons and electrons. These electrons are being added to the same energy shell and are therefore not adding another energy level. This means that we're increasing both our positive and our negative charges without increasing shielding. This increased number of protons and electrons leads to a higher effective nuclear charge as we move from left to right on the periodic table. And this concept is the reason behind many of our other horizontal trends that we're going to be talking about in this video. The trend for atomic radius comes as a result of the effective nuclear charge. As we look from left to right on the periodic table, the increasing effective nuclear charge pulls the electrons in closer to the nuclei. Because most of the atom's size comes from the electrons, this means that the atoms are smaller on the right side of the periodic table than the left. This may seem counterintuitive since we're adding electrons and yet we're getting a smaller atom, but it's because of the increased effective nuclear charge. As we look at the periodic table from top to bottom, we are increasing in size. Now we are not only adding more electrons and more protons, but we are also adding extra energy levels. This increases the shielding. The increased number of electrons combined with the shielding of the core electrons to the valence electrons leads to larger atoms toward the bottom of the periodic table. In later trends, we'll talk about many exceptions. Atomic radii do not have many of these since it does not rely on electron configuration. Let's do two examples. Pause the video now and use what we just discussed to work through these, if you're able. If you get stuck, or once you've finished, come back, hit play, and we'll walk through them together. I've circled the elements to help you find them a bit easier. For this first one, we're looking across a row. Those on the right are smaller than those toward the left. So to rank these by increasing size, we will rank from right to left. Or in other words, bromine, and then Ge, and then K. For the second one, we are looking down a group. The further down the periodic table that we go, the bigger the atoms get. So if we're going to rank in increasing size, then we're going to start at the top and work our way to the bottom. or in other words, NaSBi. Let's move on to talk about ionic radii. When we're looking at ionic radii, we need to factor in the charges along with the number of electrons and protons. If something has a positive charge, it has more protons than electrons. So this increases the effective nuclear charge, making the ion smaller. The higher the positive charge, the smaller the ion. So, for example, copper 2 plus is smaller than copper 1 plus, which is smaller than neutral copper. If an ion is negative, it has more electrons than it does protons. This gives it a lower effective nuclear charge. The electrons are not held as tightly, and the ion is bigger. So, for example, sulfur 2 minus is bigger than chlorine minus. Generally, the charge makes a bigger difference than the location in the periodic table, though of course for extreme cases that might not be the case. Look at each of the following examples. Pause the video now and try to work through them yourself based on what we just covered. Come back when you've finished or when you need some help. How'd you do? For the first one, the charges are all different, and so we can rank in order of charges. Be2 plus has the highest positive charge, and so it's going to be the smallest. And then Li plus, and lastly F minus, with the negative ion being the largest. For the next one, we can rank the copper ions in order of charge, like we talked about in the explanation slide. But then we'll need to look at our periodic trends for atomic radius to tell the difference between copper 1 plus and potassium 1 plus. So we can see that copper plus is further to the right, and so it's going to be smaller than potassium plus. This gives us copper 2 plus as the smallest based on charge, copper plus smaller than potassium plus based on the atomic trend. Now let's move to the third one. Each of these had the same charge. So we're going to base this on the same trend as the atomic radii. The charges are all going to have the same effect of making the atoms or making the ions bigger. And so we can just look at the trend based on our effective nuclear charge and our shielding. So this gives us fluorine as the smallest because it's near the top of the periodic table, and then chlorine, and then finally bromine. Let's move on to our next trend, ionization energy. Ionization energy is the energy required to remove an electron from its ground state configuration. The tighter the electron is held due to effective nuclear charge, the harder it's going to be to remove it, and therefore the more energy that will be required. So as we look from left to right on the periodic table, our effective nuclear charge is increasing. It's getting bigger. This holds the electrons tighter to the nuclei, and therefore the ionization energy increases because it's going to take more energy to remove that electron. As we look at the periodic table from top to bottom, we see that the molecules are getting bigger due to shielding. This shielding means that the valence electrons are feeling the nuclei less and less as we move down the periodic table. This means that as we go down the periodic table, the ionization energy is going to decrease. It's going to be easier to remove that electron. This is the main trend, but there are several important exceptions that you absolutely need to know. So let's look at those now. This is so important that even though I said it on the last slide, it gets its own slide with really big letters to help us draw attention to it. Our exceptions come from half-filled p subshells and fully filled s orbitals. These exceptions arise because when we remove an electron, we change the electron configuration. Unlike our previous trends, ionization energy relies on the stability of electron configurations as well as effective nuclear charge. It relies on both effective nuclear charge and the stability of electron configurations. If a particular configuration is very stable, such as in the case of a fully filled s orbital or a half-filled p subshell, it's going to give it a slightly higher than expected ionization energy. So let's look at these examples. Here's a graph of all the ionization energies, and I've drawn attention to a few places where we're going to look at these exceptions. If the trend was stable, you would see a straight line going from here up through here. You wouldn't see this flip-flop that occurs right there. Now, let's explain this. I want you to take a moment, pause the video, and write out the electron configurations for the 4 elements that I have listed here. While you're doing this, what do you notice about their electron configurations? And then how does this relate to what I talked about on the last slide? Come back when you're either finished or stuck and need a bit of help. Okay, let's look at these together now. If we write out our electron configurations, you can see that in each of these pairs, there is a flip-flop on the trend, here and here. Having a fully filled s orbital, like we do for beryllium, or a half-filled p subshell, like we do for nitrogen, makes that electron configuration more stable. It's going to be harder to remove an electron from that stable configuration than it is from the configurations like boron or oxygen, which has this one extra electron past that stability point. And so this part of the table flip-flops in order of ionization energy. Note that even though this does provide an exception, it's not like an enormous one. Beryllium doesn't suddenly jump higher than fluorine or anything extreme like that. It's a pretty subtle difference. It's only really enough to flip-flop one element. So oxygen now becomes less than nitrogen, but nitrogen isn't suddenly higher than fluorine or, goodness, a noble gas like neon. It's not that extra. It's not that much more stable. Let's do an example problem. We know that the trend for ionization energy increases from left to right. I want us to rank the entire second row by increasing ionization energy. Now, let's say there wasn't any exceptions. What we would do is we would just rank them in order, right? We would rank them like this. And this is sort of the most common wrong example, where when people are ranking anything within a row, they forget about the exceptions and they just rank in order of the trend. So we have to remember that these exceptions occur when we have a full s orbital or a half-filled p subshell, and that those are going to be a bit higher. So let's highlight those. Beryllium gives us a fully filled s orbital, and nitrogen gives us a half-filled p subshell. So these squared elements are going to be a little bit higher than we would expect. Not a huge amount, just enough to kind of switch with their nearest neighbor in the periodic table. So this one isn't right. We need to switch beryllium and boron because beryllium is going to be just a little bit harder to remove that electron than boron. And then we're going to need to switch the nitrogen and the oxygen because nitrogen is going to be just a little harder to remove that electron than oxygen. So those are going to be unexpectedly high. A good take-home example at this point would be to do the exact same thing that we just did here for the second row atoms. Do the same thing for the third row atoms, okay? And then check yourself by looking up the values. Electron affinity is an energy measure of how likely an atom is to get an electron. This turns a neutral atom into a negative ion. Notice, like ionization energy, this changes the electron configuration of the species, and therefore we have to account for electron configurations when discussing the trends. The general trend for electron affinity is that it increases as you go up the periodic table and to the right. The underlying cause of this is the same as our other trends. As we go across the periodic table from left to right, the effective nuclear charge increases. This increasing effective nuclear charge is felt by the other electrons nearby as well. And so they're likely to be pulled toward the atom. As we go down the periodic table, increased shielding from the core electrons cause the valence electrons to feel the nucleus less. And this is true for nearby electrons as well. And so they are less likely to be pulled toward the atom. Or in other words, they have a lower electron affinity. Just like with ionization energy, we have to account for exceptions. And though the direction will be different for this one, the exceptions exist for the exact same reasons. When s orbitals are fully filled, or the p subshell is half filled, we are at a stable electron configuration. And so just like in ionization energy, when it didn't want to lose an electron, it also doesn't want to gain an electron. And so it decreases the electron affinity. Let's do the same example problem, but now we're going to be ranking them in order of increasing electron affinity. We know the trend is increasing from left to right. So as we move across the periodic table towards the right, in general, we're going to increase electron affinity. So if there was no exceptions, well, it would just be listed out in order. And this is your most common wrong answer. When we ask for any rankings within the third row, or the second row, or within any row, I suppose, people will often forget about these exceptions. So we have to remember when we are at a full s orbital or a half-filled p subshell that these are going to be a bit lower than expectations. So notice that's different than the last time we did this, because when we did this before, we were talking about ionization energy. Now we're talking about electron affinity. And so it doesn't want another electron, and so it's going to have a lower than expected electron affinity. Now, it's not going to be tremendously lower, just a little bit. Just enough that it's going to switch spot with its nearest periodic table neighbor. Okay, so since we're doing this with the whole row, we can see that beryllium and it's going to go one less, so it's going to switch with lithium. And nitrogen is going to go one less, and so it's going to switch with carbon. And we get this ordering. All right, so whenever you're asked to rank anything in order of ionization energy or electron affinity, you need to check for these exceptions. We saw when we did this last time and it was ionization energy, it switched towards the right because it was a higher ionization energy, because it took more energy to remove an electron. But now when we're talking about electron affinity, it has a lower than expected electron affinity because it doesn't want to get another electron. And so it's going to switch with its nearest neighbor to the left. Electronegativity is often talked about in the bonding sections of the course and not the periodic trends section of the course. But I think that it needs to be talked about in periodic trends as well. Electronegativity is the ability of an atom to attract electron density within a chemical bond. It increases as we move to the right on the periodic table due to increasing effective nuclear charge. And it decreases as we go down the periodic table due to increased shielding. So this is for all the same reasons that we talked about with electron affinity and ionization energy and atomic radii. Now, there is definitely some similarities in the concepts between electronegativity and electron affinity. But notice something looking at the two charts. Electronegativity doesn't have very many exceptions. So few that we're actually, the ones that do exist, we're not going to worry about talking about it in Gen Chem. So take a moment, pause the video, and think about why this might be. Why does electron affinity, which is the ability of an atom to attract an electron, have all these exceptions, but electronegativity, which is the ability to attract electron density in a chemical bond, doesn't? Come back when you're either stuck or you have thought about an idea. So the answer to this is that there is one big difference between the two. When we're talking about electron affinity, we're talking about it attracting an electron, which changes the electron configuration. The stable electron configurations then cause these exceptions. But for electronegativity, all of the atoms are bonded already, and so they're already in a stable electron configuration. And the only thing that matters is the effective nuclear charge and how that is affected by shielding. To wrap up our discussion, let's revisit this picture. Here we see all of the periodic trends that we discussed, and each arrow shows which direction leads to the increasing periodic trend. You'll need to know each of these trends throughout your science careers. Understanding the reasons behind them will also help make all the future topics that use these as a prerequisite to be able to comprehend, remember, and use. So ensure that you know not just the trends, but you know the common exceptions that you need to know, and then you know the reason behind each of the trends and the reason behind the exceptions. And you can review this video as much as you need in order to get each of those.